Hello everyone, and welcome to a midterm question. So, as you guys probably already guessed, I'm solving a couple of the midterm questions, ones that'll be more applicable to the midterm that you guys will be solving coming up. And to start off the 2013 midterm, we're going to be looking at question 1. So question 1 is kind of iffy, if you ask me, because it does involve some force reduction, which will not be on the midterm. But it's a good idea to kind of see how we get to some of that force reduction, because force reduction involves a lot of taking moments, finding position vectors, stuff like that, and that will be on the midterm. And especially question 2, where it says the angle between two vectors. And that's very, very, very important, because even though force reduction may not be on the midterm, angle between two vectors is completely fair game. So let's just kind of begin. We'll go through the questions. And remember that the midterm is going to be 2 hours. So each question should take you roughly half an hour. I'll probably take longer than that because we're going to try and explain things. But the main goal of this isn't just to show you kind of the straightforward solution, but to also show you maybe some tricks that may be involved, because that's typically what'll make or break you in the midterm, is if you know some of the tricks that'll help you solve questions a bit faster. So let's just take a look at this question. So it says, as shown in figure 1a, 5 forces act on the triangular prism. Okay, well, we look at 1a, and you're right. We got a triangular prism with a crap load of forces, so it doesn't look too good right now. And the first part of the question says, those 5 forces can be reduced to an equivalent force couple system as shown in figure 1b. Determine FR and MR and express them in Cartesian vector forms. So this is where midterms are kind of mean in a sense, because the first question that they ask you is to take all of those forces and put them into one force. And originally, well, you guys know how to put forces together, but what kind of the mean part is there's 5 forces. 5 forces here. So a lot of people just look at this real quick, and they're going to look at the prism and they're going to become overwhelmed. And that's one of the worst things in the midterm, is just you become overwhelmed. And when you're overwhelmed, you can't think straight, and then you start making silly mistakes, stuff like that. So the best piece of advice, especially on question 1, is just relax, calm down. Everything is going to be fine, because you guys know all this stuff. You guys know all the steps. It's just a matter of relaxing and just looking at the question. And usually what happens, and you'll see that in this case a lot, big time, is they always contain tricks. It always looks overwhelming, but if you know the right tricks, it's actually very, very, very simple. Very simple. So let's go through real quick. And let's solve part A of the question, and we can see if we can find some tricks. So what I'm going to do is part A, and we know that part A wants 2 things. It wants the resultant force and the resultant moment. So let's just go resultant force first and just look at it. So resultant force. And we know the resultant force, well, there's a couple ways we can do it. We know that for 3D, typically, the best way to do it is get all those forces in Cartesian vector notation, and then add them all together. So we'd have the resultant force is equal to F1 plus F2 plus F3 plus F4 plus F5. And that's quite a mouthful. And this is why it starts to overwhelm people, because they're going, oh my goodness, I have to add 5 forces? That's too much. That's too much. So let's see if we can find some tricks really quick. Now let's start off and look, okay, well, we got FC that acts kind of at a diagonal from C to B. Well, that doesn't look like a trick. That just looks like a vector. So let's just leave that for now. Now, this is where it starts to get interesting. If we look at the other vectors, we can see right away that 2 of the vectors are exactly the same in magnitude. So let's look at the 25, for example. We got 25s, 2 vectors. But what's really interesting is if we look at the direction, one of them is going straight up and the other one's going straight down. So if I were to express these both in Cartesian vector notation, what we'd find is the 25 going up would be 0i plus 0j plus 25k. And on the other hand, the other side would be 0i plus 0j minus 25k. And we find that if we add those 2 together, they're just going to cancel each other out. So real quick, we can kind of make one thing. We can go the 25 kilonewton forces cancels out. Forces cancel out. So if we're looking at the resultant force, we don't have to worry about those 25 kilonewton forces. They cancel each other out. The resultant for them together is 0. So they don't even contribute. So right now, real quick, when we're looking at resultant force, we can just almost cross them off. They cancel each other out. They'll have no effect on the resultant force. Now, let's look at the other ones, and it's kind of the same thing. We got 120 and 120. And if you look at the directions, again, they're completely opposite, and they go in the y direction. So for the 120 kilonewtons going to the left, its force vector, of course, would be 0i minus 120j plus 0k. And then the other one, the one that's going to the right, would be the opposite. So they would also cancel out. So right here we can put the 120 kilonewton forces cancel out. And now you guys can see why, oh, this is where the midterms create all the tricks, because originally we looked at the question and we said, okay, well, we got to add 5 forces together. But after we cross out the 125s like we just did, we realized that there's only one force left. So therefore, we can conclude this. The resultant force, Fr, well, that's just going to be equal to force C. Now, the question's not as easy as just saying it's equal to force C, because again, we need to take that force, and the question specifically asks, and I'll highlight it right now, express them in Cartesian vector forms. So we have the magnitude of Fc, which is 300 kilonewtons. However, that's not Cartesian vector form. But we know that we can find its Cartesian vector form, so Fc with the arrow, its Cartesian vector form, by if we take the magnitude of Fc and we multiply it by the unit vector of its direction. And if we look at its direction, we know that this unit vector, or the force vector itself, goes from point C to point B. So what we can do is we can write the unit vector from C to B. So it goes from point C to B. Well, now we got to ask ourselves, okay, well, we have the magnitude of Fc. We know it's 300 kilonewtons. That's pretty easy. But now, how exactly do we find the unit vector CB? And there's usually 3 different ways. The first way is trig. And it's very obvious when you get trig, they give you a bunch of angles. And those angles, very, very rare, because it goes down to trig. You guys know trig. We're not trying to test you really on your trig skills. We're trying to test you on your vector skills, vector addition, stuff like that. So trig is very rare. The second case, which is more common, would be coordinate direction angles. So that's that alpha, beta, and gamma. We look at this question, we don't have alpha, beta, gamma. However, we have the third case. And if you guys remember the third case, it's coordinate points. So remember, we can find the unit vector if we know the position vector between those 2 points. So if we're looking at the position vector, which would be RCB, we know we can find that if we take the coordinates of B and we subtract the coordinates at C. Okay, well, now we're just going to have to find those coordinate points. So if we look at RB, we see B is right above the origin, so we know its x and y are going to be 0 and 0. So 0, 0. And if we look at its z component, we see that it's 2 meters above the origin. So we're going to put 0, 0, 2 in the bracket. And we're subtracting the coordinates at C. And if we look at C, it's 4 meters in the x direction and 4 meters in the y direction. So we're going to have 4, 4, and 0. And these all have units of meters. And what we'll find out is once we substitute all of that in, we're going to get negative 4i minus 4j plus 2k. And that makes sense because if we look, oh, and sorry, it has units of meters. And that makes sense because if we were to go from point C to point B, we know we have to go negative 4 steps in the x direction, negative 4 steps in the y direction, and then positive 2 steps in the z direction. So I'm just going to put RCB. Now remember, to find the unit vector of this, we're also going to need the magnitude of RCB. And that's easy to find because we know that the magnitude of a vector is going to be all of its components squared, added together, and then square rooted. So even though that sounds like a mouthful, what it basically is we're going to take the I component squared, so we're going to have 4 squared plus the j component, so plus another 4 squared, and then plus the k component, so a 2. So plus a 2 squared. And I'm just going to finish the square bracket real quick. And what we find is this is equal to 6. And the units for this will also be in meters. And what the magnitude represents on this diagram is that is the length from point C to point B. So if I take a tape measure, put one end at B, and put the other end at C, I'm going to get 6 meters. So now we can find the unit vector CB. So U, CB, because we can just take the position vector CB and divide it by the magnitude of CB. So just like this. So we're just going to take all of those components, the -4s, the 2's, and we're just going to divide it by 6. So what we're going to get when we do our vector is the first one's going to be -4 divided by 6. Well, that's -2/3. So we're going to get 2/3 of I. And for the j component, it's actually the same thing. So minus 2/3 of j. And for the k component, we have a +2. So 2 divided by 6, well, that's just 1/3. So we're going to go plus 1/3. And that's in the k component. So we can finish this up and the brackets. And remember, unit vectors do not have units. And it makes sense because take the I component, for example. We're dividing meters by meters. The meters cancel. We're just ended up with a single number, and that's it. So finally, we can go back up, and we remember that FC in its Cartesian vector form is going to be equal to the magnitude of FC, which we know is 300. And we can multiply that in to the unit vector. So we got -2/3I minus 2/3 in the j plus 1/3 in the k. And remember, the unit vector doesn't have newtons. Doesn't have units, but the magnitude of the force vector will have newtons. So when we multiply the 300 into everything, we know that that's where the units of newtons will start coming in. So first component is just going to be 300 times -2/3. Well, that's just -200. So we're going to have -200 in the I direction. The same thing for the j. So we're going to have -200 in the j direction. And we're going to have plus 100 in the k direction. So we can end that. And the brackets, remember, these ones will have units of newtons because it's a force vector. And as we said before, our Fr is actually equal to Fc because all the other forces conveniently canceled. So what we can say is that Fr, so this is the resultant force, is equal to, and we can just put what Fc is because we know it's equal to Fc, so it's going to be -200I minus 200J plus 100K. And we can end those brackets. And of course, do not forget units. You will get marks taken off. So in this case, it's actually not newtons. I was actually kind of an idiot. This is in kilonewtons. So it's very, very important to keep track of units because even I forget. So what I can do, this is a final answer. So even if you guys didn't want to do it on the labs, please do it on the midterm. It's very, very important that you make it very clear which one your final answer is. So if we look up at the question again, what it says is it wants to determine the resultant force and the resultant moment in Cartesian vector form. And what we just did is found the resultant force in Cartesian vector form. So that's done, but we're not done yet because remember, it also would like the resultant moment. So I'm just going to put resultant moment. All right. Well, as we learned from the first one, there was a crap ton of tricks in this question that made it look really difficult, but it was actually really, really simple once we knew all the tricks. So sure enough, it's probably going to be the same for moments. Probably going to be the same. So let's look at the first one, and that is the 25 kilonewton forces. Well, if we look, we know that they cancel an x. They're the same magnitude. Oh, but they're also the same direction. And this will not be on the exam because we've covered it in class. You guys know what I'm going to say, but it will not be on the exam. But what happens here is those 25 kilonewton forces, they're equal in magnitude and they're opposite in direction and they're parallel to each other. So what we know is those would actually create a moment, a couple moment. So I'm just going to write here the 25 kilonewton forces create a couple moment. create a couple. I'm just going to put couple. You guys know what I mean. And remember that we can find the moment due to a couple. So I'm going to put MC. Actually, I'm going to erase the C because that's we're going to leave that as the forces C. So I'm just going to put M1. So this is due to the 25 kilonewton forces. And we know that it's going to be equal to the force times the perpendicular distance between the two. So we know that the force is 25 kilonewtons. And we need to find the distance between the two. So if I'm looking up at this diagram, the perpendicular distance between the two is going to be this distance right here. So if I look at my nice triangle, I can look at the bottom and I can tell that that distance is going to be 4 meters. So what I can do, I can come all the way down. I'm going to put 4. So I know that the moment couple is 100 kilonewtons times meters. But we're not done yet because I left a space there, and as you guys can guess, moments have signs. Negative, positive. We're going to have to figure that out. So I'm going to erase this pink again real quick. Oops. There we go. Erase the pink real quick. I'm going to go back to the pink, and we're just going to look at the general consensus of these. So if the left side's going up, the right side's going down, we know that the rotation is going to be something like this. Now, if we look at that rotation, it's actually clockwise. That's a clockwise rotation. So we know that the moment here, the couple moment, is actually going to be negative. And I forgot the meters. All right. It's going to be negative. Now, here's another problem that we have. We have this moment as a scalar, which is fine. But when we're going to add it to the other moments, we have to remember that we're going to need it in Cartesian vector notation. So now we know that M1, we can actually find it as a Cartesian vector. But we just have to figure out, okay, well, we have a negative, oops, sorry, zoomed in. We have a negative 100 kilonewton meters. What axis does that act around? So we know that, okay, well, this 25 kilonewton meters, it is in the ZY plane. So you guys should know, and this is a very important fact because it's a trick that they do basically every midterm you will ever see. If a moment is in a plane, so in this case the forces are in the the YZ plane, the moment created by those will be in the perpendicular axis. So if I'm going to go right here, I'm going to go forces in forces in YZ plane. Therefore, we know that this is the moment in the X axis. So it's very, very important. Whatever plane your forces are in, your moment will be about the axis that's perpendicular to that plane. I know I probably explained that pretty bad to start off, but hopefully you guys get the point now. So if I were to write M1 in Cartesian vector notation, what it would be is negative 100I, because if that's in the YZ plane, we know that the negative 100 is in the X axis, and then there's going to be no moment in Y, so 0J, and no moment in the K axis, or the Z axis, so plus 0, and that, and I can go kilonewtons times meters. But we're not done yet. We know that there's other forces. So what's going to happen is we look up here. I'm just going to erase the pink real quick because we're not worried about that anymore. And let's look at the 120 kilonewton forces. So, okay, well, if I'm looking at point O, they're definitely going to create a moment. And what's going to happen is the moment from this side, so on the left side, we know it's going to be 120 kilonewtons. And it's going to be times that distance. So the perpendicular distance between the force and O, so it's going to be this right here. And we know that that's times 2. So it definitely creates a moment. And if we look at the sign of this moment, well, we're going to see that it's going to go counterclockwise about O, so it's going to be positive. And if we look on the other side, it's going to be 120. And the distance is also 2. However, this is going the opposite direction. So what we find here is that this moment will actually be negative. And since both of the forces are in the YZ plane, those will both be the moment about the X axis. So those will be mx for both of these cases. And what we find is if we add them together, they're going to cancel out. And it makes sense because one of them wants to rotate it one way, the other force wants to rotate it the other way. So it's only logical if they cancel each other out. So right here, I can write that the 120 kilonewton meter, oh sorry, not kilonewton meter, 120 kilonewton forces, let's go force moments, cancel out. So therefore, we don't even have to worry about those 120 kilonewton forces because their moments are just going to cancel each other out. So now do you guys see where the tricks are coming? I've already solved 4 out of the 5 forces, and I haven't had to touch the dot product yet. Another dot product. Yeah, I shouldn't have. When you're dealing with moments, you really shouldn't touch the dot product unless you want to find a projection. I didn't touch the cross product is what I meant to say. But now, I'm not going to get so lucky. I'm going to look up, I'm going to say, okay, well, FC is going to create a moment about O, and that one will require the cross product. So if we go down here, we're going to go, I'm going to put M2, so this will be my second moment. And this is going to have to do with a position vector, cross, and we know that our force vector is going to be FC. So we already know FC in Cartesian vector notation, so that's not really a problem. The question is, what is the position vector that we're going to need for this one? So if we look up here, remember that a position vector has to start, it has to start at the point which we want the moment about. And in this case, we're taking it about O. Right here. So, it starts at the point which we want to take the moment about, which is point O. However, it can go to any point on the force vector. Any point. So we got 2 options actually. We can go from O to C, a position vector from O to C, or we can go from O to B. Now, it's really up to you what you pick. You'll get the exact same answer. But for me, I'm picking O to B. And you go, okay, well, Clayton, why did you do that? So I'm going to put this right there. I'm going to have this as my position vector, OB. Why did you pick that and why didn't you pick C? And it just has to do with what I think might be the easiest. So if I look at the coordinates of B, 2 of them are 0. X is 0 and Y is 0. If I look at the coordinates of C, on the other hand, I only have one of them that's 0, and that's in the Z direction. So point B just has more zeros. I assume it's going to be easier. So if I go down here, what I'm going to do is I'm going to put OB. All right, so we can start to solve for this moment once we know ROB. So we can say that ROB, well, we know that to find that, it's going to be the coordinates of B minus the coordinates of O. But since we know that O is the origin and just 0, 0, 0, we can cancel that out right now as 0. So we know that the position vector ROB is just going to be equal to the coordinates at B. So we already know the coordinates of B are very simple because there's 0i plus 0j and then plus, I believe it's 2. So let's just take a peek. Yeah, it's a distance of 2 meters up. This is the z-axis. So we're going to put plus 2k and the brackets, and this will have units of meters. And what's nice about the cross product, remember, is we don't need to find a unit vector, find a magnitude. We just need the position vector. And we have that. We also have the force vector C. So what we can do is we can go equal, and we can start creating that nice matrix. So what's going to happen is, remember, the first row of this will always be ijk. Always. There's never an exception unless you're doing the triple scalar product, which I almost don't recommend. If there's ever a question like that, I recommend just doing 2 steps, my opinion. The second row will always be our position vector. So in this case, we have 0, 0, and 2. And this is why I picked point B, because the other way, I would have 4, 4, and 0. And those 2 4s just make it a lot more inconvenient. I'd rather have as much zeros, so as much stuff goes to 0 as possible. And then our force vector, if we look up, it's negative 200, negative 200, and 100. So we're going to throw that into the third row. So negative 200, negative 200, and we got 100. And then with all our rows, we can close this up. and we can start doing all the math inside of this. So, oops. Come on, go back. There we go. So what I teach is what I call the fish method. I have videos on that, so you guys can kind of go through it, but I'll show you guys just because it's a midterm, so we're going to go nice and easy. So what I'm going to do is, if I'm looking for the I component, I'm going to cross off everything in the I column, and then I'm going to make a fish that starts at the top left, comes down, and goes like this. And what the fish does is it tells me the order of operations. So it starts at 0, so the first component is going to be 0. And then it goes to 100, so times 100. And we go minus, and then the next one is 2. And then the last one is negative 200. So that right there is going to be my I. Now the only thing that you're going to have to remember kind of by yourself, which is very, very important, is that the J component always starts off with a negative. So we're going to go minus, then in brackets, and we're going to do the fish method again. So I'm just going to remove all this, and we're going to go back to the fish. So I'm looking for J. Well, let's just cross off everything in that J component. Now let's do a fish. So starting at the top left, we go down, we go up, and then to the other side. So what happens is I got 0 times 100 in the first one. So this is why it's nice to pick points with a bunch of zeros, because as we're going to see, a lot are just going to go to 0 and cancel. And we're going to minus, and on the other side we got 2 times negative 200. So we can end that and throw in the J. And I'm going to just erase all that crap. And then the final one, so we're going to start with a plus because it's only the J that starts with a negative. And we're going to do the fish once more. So we're going to cross off everything in the K components and draw a fish. And this one's really, really nice because as we see, there's zeros on both sides. So it's going to be 0 times negative 200 minus 0 times negative 200. And this, we can end with the K. And we're actually done our moment vector, so we can add this brackets and we can put the units, which will be kilonewtons times meters. But now, of course, that's kind of messy. Let's make this look a little nicer. So I'm going to put M2 is equal to, and we're going to do it in brackets. And the first one's going to be 0 minus, and then that number. So what we're going to have in the end is 400i. And then the second one is going to be minus 400 in the J. And then the last one we can see is going to be 0 in the K direction. So we can end the brackets. This is going to be kilonewtons times meters. Now, we're not done yet because we're done the hard step, which is we found the moments due to all of those forces. So a quick recap, we had a couple moments. So we found M1. We found out the 120 kilonewton forces canceled out, so they didn't create any sort of resultant moment. And then finally, we have M2, which we obtained using the cross product. So what we can put is MR. So this is a resultant moment. And we know it's just going to be all of our moments added up. So we got M1 plus M2. So what we're going to have is I'm just going to take those two components on each one. So looking at M1, we have negative 100. Looking at M2, we have 400. So it's going to be negative 100 plus 400, which is going to be 300i. We look at the second component. Well, M1 is just zeros for the rest. So therefore, the rest of the resultant force is just going to be M2. So it's going to be minus 400J. And then plus 0 in the K. And I can end those brackets. And I can put units. Remember, do not forget units. It'll lead to very bad things. And this is MR. So that's our final answer. What I can do is I can put a nice box around it because that is the resultant moment. So I just touch up the box. Alrighty. Alright, so not too bad. And I'm just going to erase the crap from the fish method up here because we don't need to see that. Alright, so looking at the question, what I wanted us to do is find FR and MR in Cartesian vector notation. We look here, we have FR in Cartesian vector notation, and we also have MR in Cartesian vector notation. So they're both good to go. We're going to leave them. this question, or part A of this question, is now complete. So now we're going to go to the second part, which is part B. And hopefully it's a little bit shorter because that was a lot of work for 5 marks. But we'll find out. So part B, we're going to go up to the top, see what it's asking. It says, determine the angle. And I'm going to highlight that because we know that's a very important word. Between the tails of FR and MR. Okay, well now this is very, very interesting. What it wants us to do is find the angle between 2 vectors. And if we ever have the angle between 2 vectors, so if it ever asks for an angle, we have to go to the one formula we know that has an angle, which is the dot product formula. Dot product. So, if you guys recall, and I believe it's on your formula sheet, the cosine of theta, so this angle, that theta, that's what we want. That's the angle between the 2 vectors. We can find it if we take vector A, which I'm just going to put as a lowercase a, dot it with vector B, and then we divide it by the magnitude of A times the magnitude of B. And now this is where it kind of gets a little bit interesting, is because usually what you guys would do is you can find the angle between 2 vectors, but usually the vectors are the same. We'll say find the angle between 2 unit vectors, maybe 2 position vectors. But in this case, it's a little bit different because it wants us to find the angle between a force vector and a moment vector. And they have different units. They mean different things. So the question becomes, do I have to modify one of the vectors, or can I just take this product and just pretend that they're just 2 vectors? And what the answer is you can actually take them even though they're 2 different types of vectors. It's completely fine. All the math will work out. So in this case, what we're going to want is cosine of theta is going to be equal to FR dot MR divided by the magnitude of FR. And it's nice because we already have that from the beginning of the question, and then divided by the magnitude of MR. So we don't actually know the magnitude of MR, but the rest of the stuff we actually know. So before we begin, let's just find the magnitude of MR, and it's the same as finding the magnitude of FR, where we're just going to square all of its components and then add them together. So if I go square right here, I'm going to have 300 squared plus 400 squared plus 0 squared, and that's equal to, and I'm just going to close up the bracket before I forget, and that should be equal to 500. This will be kilonewtons times meters, and this is the magnitude. So now I have every possible piece of information that I need in that formula. So it works out really well because we know that cosine of theta, and I'm just going to start throwing in numbers, just substituting everything in. So remember the dot product, what we're going to do is multiply the 2i components, we're going to multiply the 2j components, and multiply the 2k components, and then add them all together. So starting with I, I'm going to go to the top for f, and we've got negative 200. It's going to be negative 200. And then I'm going to look at the second one, and we see that it's 300i for the moment. So that's the first one. Then we're going to add. And the second, the j component for the force, is negative 200 again. So I'm going to go negative 200. And the j component for moment is negative 400. 400. And then I move on to the k component. But as we see, the k component for the moment is 0. So it's not going to have anything in the dot product. So I'm just going to leave it. I guess if you guys really wanted to, you can go plus 0. But then at the bottom, we're going to have the magnitude of the force, which we know is 300. And we're going to throw in the magnitude of the moment, which we know is 500. So all that right there, that's just going to equal a single number. So what we're going to have is cosine of theta. And after you throw everything in, what it's going to be equal to is 2/15. So 2 over 15th, 2 over 15th, 2 over 15, or 2/15. And then what we can do is just inverse cosine it, and what we're going to get is theta is equal to 82.3 degrees. That right there is a final answer because that's the angle between vectors. So we're going to put a nice box around it to let everybody know this is the final answer. We are good to go. So if we look up at B, the next thing is just read the question thoroughly. So I'm just going to make sure. All it wants, determine the angle between the two vectors. We did that. Perfect. 2B is done. Or I guess question 1B, it's worth 2 marks. So we can move on to question C. And looking up at question C, this is when it starts to get a little bit juicy. Because what it wants is it wants us to resolve MR. So we have a moment and we want to resolve it into 2 components. A parallel component, which is the 2 straight lines, and then a perpendicular component right there in the direction of FR. So this is very important. When something asks for the 2 components, it's always going to have to give you a direction on which the components are. So in this case, it wants it in the direction of FR and the direction perpendicular to FR. And then most importantly, express it in Cartesian vector forms. So let's go down here. We know that we have this moment vector right here. And what we're going to want to do is find the moment vector that's parallel to FR and the one that's perpendicular to FR. So if we draw a picture really quick, because sometimes a picture always helps. And in the midterm, you probably don't have to do this, so don't worry. It's basically what's happening is we have a moment vector, say like this. So I'm going to do this, and I'm going to put the little arrow. So that's a moment vector. And we also have a force vector, which I'm going to just kind of throw just like this. I'm going to make it extremely long, force vector. So what we want to do is we want to take this moment vector and we want to create 2 separate vectors with it. So we're going to project it right here onto this. So this right here, this vector, this will be our MR. Oh, so I should put R here, sorry. This right here is going to be MR parallel. And then the perpendicular one is the one that's going to go straight up and across. So if you look at this, it's actually just like finding X and Y components, basically. So MR parallel, and if that's the parallel one, this is going to be MR perpendicular, because this is going to be 90 degrees between the 2. And I should put the little arrows to show that they're moment vectors. So this is all we're really doing right here, is trying to find those 2 components of MR. And it's very, very easy to do because we can use the dot product again. So what will happen is the magnitude, and this is very important, the magnitude, not the vector itself, but the magnitude of MR parallel is going to be equal to our moment vector, so MR, and then we're going to dot it with the direction that we want. And this is why I said in the question, they have to give us the direction. And the direction will always be a unit vector. And in this case, it wants the direction of FR. So I should probably put FR. And since we know FR is equal to FC, this will be the unit vector that we used up above when finding FC. So if we go to the top, we know that it's going to be UCB. So right here I can put UCB. And then what can happen is I'm just going to take all those components and it's just the dot product. So I'm going to take the 2 Y's and multiply them, the 2 J's and multiply them. So let's take a look at the very top. Oh, sorry. I guess we start here. So the I component for the moment vector is going to be 300. So what we're going to have is 300. Then we're going to take the I component of the unit vector. So we're going to scroll all the way up again. And what we see is it's negative 2/3. We're going to go all the way back down. We're going to put negative 2/3. And we're going to add the 2 J components multiplied by each other. So if we look up here, it's negative 400 for the moment. And we also have negative 2/3 for the unit vector. And then, as always, the third, the K component for the moment 0, so we can just leave it at 0. So what will happen is when I do all of this right there, I'm going to get 66.67 kilonewtons times meters. So remember, this should be a single answer because we just found the magnitude of FR parallel. We did not find the vector of it. We found the magnitude of it. But that's completely fine because remember, we can find a vector. So in this case, we want MR parallel if we know the magnitude, which we do. So MR parallel, the magnitude, and then we have to multiply it by its direction. And what's nice is its direction is going to be the same as F. So this is going to be UCB. So all I'm going to do is take that 66.67 and I'm going to multiply it into the unit vector CB, which is right here. So the negative 2/3, minus 2/3, and then plus 1/3. So what will happen is I'm going to get this. Is MR parallel as a vector is going to be equal to, and the first one again is, like I said, I'm just going to take that negative 66.67, or sorry, just 66.67, and times it by negative 2/3. So I'm going to get 44.4 in the I direction. It's going to be the same thing for the J, the J direction, so negative 44.4 J. And then for the last one, I times the 66.67 by positive 1/3. So I'm going to go plus 22.2, and that's in the K direction. I can end this, and of course the units will be kilonewtons times meters. And that's one of the answers. Remember, it wanted MR parallel. So I got that. I can put the box around it. So let's try and make it somewhat nice. So this is done. MR parallel is done. But now we got a problem because the dot product works really good finding the parallel components, but it doesn't really help us find any perpendicular components. So now we got to ask ourselves, okay, well, how do we find MR perpendicular? And this is when your 2D intuition has to come out and play. Because we know that in X and Y components that a force vector is made of the X component with the Y component. So X plus Y. So it's the same thing here is this moment vector, our resultant moment vector, which we know that that is equal to the moment vector parallel, which we also know, plus the moment vector perpendicular. And if we look at this, the only thing that we don't know is actually MR perpendicular. So therefore, we can find MR perpendicular by just doing a little bit of algebra. And what we're going to do is we're going to move the one moment to the other side. So it's going to be MR minus MR, oops, not perpendicular. That's what we're solving for. MR parallel. So what we can do is just throw in the parallel. We know MR. We know MR parallel. So it's just vector subtraction. So therefore, we're going to get MR perpendicular is equal to, and I'm going to do the squiggle brackets. So what's going to happen is I'm going to take the value of MR. So if I look at this, we know that MR, the I component, is 300. And we're going to subtract the I component of MR parallel, which is negative 44.4. So what we get is 344I. And then for the second component, we're going to get minus 356 in the J. And then we're going to have minus 22.2 in the K. So I can end this, and I'm going to clean that up after, but it's going to be kilonewtons times meters. So let's just erase this real quick because that looked terrible. Do this. And just as a quick reminder where I get this number from, so the 344, it's going to be MRX, which is the 300. And then minus, and then the MR parallel X, which is the negative 44.4. And if we get that, we get the 344I. So I'm just going to erase this real quick because remember that MR perpendicular, that's our answer. So what we're going to do is we're going to throw a nice box around it. This won't work at all, will it? Yeah, nope, that did not work. All right, let's try this again. Oh, that one worked just fine. So this is our final answer. And what I can do now is I'm just going to put the purple over top to show where I get this value from. Like this. But that's the second part of the question. So that's part C. So if we look at part C, we again double check, make sure you guys know exactly what you guys were wanting. It wanted MR in two components, MR parallel, MR perpendicular. Well, we did that. And just said make sure that it's in Cartesian vector notation. We check. Oh, they're both in Cartesian vector notation. They both have units. We're good to go. And that right there concludes the very first question of the 2013 midterm. So, as you guys will see, what they like to do, overwhelm you. 5 forces. 5 forces. And when you see that, you're thinking, oh crap, that's a lot. But as you guys can see, a lot of them canceled out. A lot of them create a couple moments, but again, couple moments won't be on the exam. But it's just this kind of methodology on just trying to look for those little tricks. So that concludes question 1. I will see you guys in question 2.